Thank you, Monica. Thank you, Monica, for your nice and kind introduction. And also thank you very much for your invitation, for giving me the opportunity to present your DNRF microscopy facility. So we can see the title of my presentation, FT002 in an aberration transmission electron microscope. So there is a brief outline of my presentation. So time is short. It's a collection of many slides which I already have in presentation for our microscopy conferences and also many workshops and meetings at Electron. So there are a lot of details. Actually I'll go through only the important points and also highlights for the results. In this field. So my plan is to start with the basics. Basically, what is phase contrast microscopy and how we do phase contrast microscopy in TEM, Electron. And a few slides for the special resolution. And then on this going to aberration, various kind of aberration characters that we need to understand before using aberration microscope. And what we can do with this kind of aberration microscopy, particularly negative phase contrast microscopy, for direct imaging of atoms and also direct intuitive interpretation of materials. But if we want to extract more information about the materials, for example, how that want to say which atom is what, we want to extract information on the potentials of the objects and white out. No, we have to do actually extensive education in the construction. So I'll go through also briefly this image simulation and specific topics and also our contribution. While we are doing some work in this area. And some of the points about, some of the groups that we are thinking, what we can do actually in this kind of microscopy, it makes sense the power have. On the phase contrast that we discovered, as you might be knowing, majority case, and also when we awarded Nobel Prize in Physics in 1953, I borrowed these figures and diagrams from his Nobel lecture, which was published in Science in 1955, which is really available. So you can see, if you don't do any chemical staining in the biological sample, and in the comparison between a bright field and the phase contrast image of the tissue samples, so you can see a lot of details if you look at contrast imaging compared to the bright field image. And he explained actually this phase contrast in the help of this phasor diagram, the complex diagram. As we all know, actually, the horizontal axis actually is the real axis, and the vertical axis and the y-axis actually not shown here, is the imaginary axis. So in the MV prime actually has the vibration of the waves. So horizontal component is the amplitude, and the angle on the horizontal axis is the phase. So if you are doing chemical staining or exactly on the amplitude contrast, so here MV is the illumination. So it changes from MV to MD, and the compounding is MV prime. So you can see actually featured dark in a white background. So this is your amplitude contrast. But if you have typically for density varying sample or the phase sample, so you basically change the illumination from MA to MD, and the compounding is MD prime. So you won't be able to see this effect directly unless you rotate the phase MA or MD to MGH. To be able to basically one contrast or contrast into the amplitude contrast. And this is actually done with the help of Ranjan phase split. So he made use of metallic film to basically introduce phase contrast. And this phase contrast microscopy in optical microscope are available in many biological laboratories. But in TEM, so this particular slide will come back at least 3 times because I have to make 3 different points during my presentation. So there actually geometrical phase split is not available so far in TEM. So it makes use of the CS or the quarter spherical power aberration coefficient and the T focus delta F in the form of PCTF for space contrast transfer function to introduce basically the phase shift in the electron. And they will be able to see contrast. So we make use of the PCTF function both for uncorrected and also corrected microscope to introduce phase contrast. And the other part I'll come back after some slide on a different topic. Some examples from our own group and also literature. I mean, HFTM means we basically understand the periodic arrangement of white dots. In fact, white dots that represent the periodicity of the crystalline structure of any material of high symmetry orientation. So this is actually inorganic. So these are inorganic compounds, thin film nickel ferrite, which are on 0, 0. So we can basically inverse to the structure of the cubic structure. And this is an example of MOS2 RDS to 2D alloy, where we can see the structure of 2H1T. So you can directly visualize the periodicity of the atomic arrangements in the system and see actually how the structure changes from one to another. And this is the thin film of MOS2 on sapphire. So you can see directly how atoms are binding to the sapphire substrate at the interfacial region, and also how atoms are stacked along the brake directions. So all this information you can basically directly obtain if you are going to imaging. And at the bottom right corner, you can see another example. This is the HFTM. So this is the infrared imaging, and the reason I'm showing actually, this technique also will give you this kind of periodic white dot, and this periodic white dot also represents the structure of the material. But at the same time, this technique also can show basically some of the dots are brighter, so you can see single dopants, and you also can simultaneous spectroscopy techniques and all for the electronic structure. So the reason I'm showing actually this slide here, because HFTM actually is nowadays capable of also telling you the type of atom and also to tell you the electronic structure. I mean the bonding, what kind of bonding actually is happening if there are some dopants or defects. Returning atoms. So I'm giving some of the examples from literature. This is a picture from book actually, because if you are doing regular HFTM, I mean, you don't do any quantitative work, you are setting up the microscope nicely. Say for example, nanomaterials, you can see size of the nanocrystals, you can see crystallinity, you can see acids. These are actually the clean application of the HFTM, and here's the example of carbon nanotube. So if it is a single one carbon nanotube, you can see actually the one single wall of down and so basically all the clean application of HFTM. This example I show actually as an example from the biological molecule. So this is a very old image for 2015. So here single strand of DNA is imaged directly by cryo-EM microscopy, and I cannot see some of the text also in the presentation. You can see. So you can see where you have difficulty actually forming crystal structures to do extreme crystallography. So there actually HFTM is very helpful to visualize actually the structure directly. So you can basically get more information, for example, multiple protein configurations, and the crystal size not basically enough actually to get such interaction data. So I'm sure there are nowadays a lot of good pictures will be available, but this is an example from 2015. I also use these images for my class and have some of the presentation. This is showing. We want to tell that there are two competing phase contrast techniques and that is the resolution. One is the HFTM that I have been working in JNC. So this is actually equivalent to inline hologram. So any T-focus HFTM image is inline hologram. And also there is contact silicon photography. So with the help of two bioprism, both the techniques actually have this adequate resolution. the development of both instrumentation and also methods have been part of the writing of program and part of the sub and structural characterization of the material. So here structure means not only the atomic arrangements, but also the electronic structure, some of the examples. So both things are arranged so that you can basically get to know about the material very. And both the techniques actually they try to retrieve the missing phase information of the form space. And I'll show you actually going to do any quantitative work. Here, a lot of image resolution and very conceptual work to retrieve the missing phase information. That is just basically telling the kind of atom and the electronic structure about the material. The definition of spatial resolution. So the spatial resolution is to be able to distinguish between two dots lines. So it is minimum separation distance C. Because of the human eye can see max 100 micrometer. But if you see anything like that, you have to take the instrument, for example, microscopy, and you have to see nanometer microscope. But because of the way the electron or the light is used in this instrument, point is always blurred for instance, with this very pattern. And the radius of the disk given by this equation, 0.61 lambda was inside beta. Average wavelength, so you can see actually to use high energy electron, or if you want to reduce wavelength, you can basically increase the resolution. Use and beta gains the numerical aperture. So, but for any practical microscope, you have to limit the size of the aperture, so you cannot basically extend it very far. But you can basically improve it by having regular aperture resolution. And this criteria of resolution is given by actually the minimum separation distance that it can be found. But it shows a daily pattern. It is typically defined as the meaning of one pattern falls right through the maximum second pattern. It's not straight criteria. We can really have a little bit, full resolution by adjusting this criteria. Again, coming back to the same slide. Because we have in TEM, we are limited by aberration, so we don't have perfect length. So in the case of aberration, we define resolution by the first 0 plus 0 basically GS. And GI is the information limit. So the equation between GS and GI actually is not directly accessible. So we have to take help from various image sequencing techniques. We extract information between GS and GI. And between GS and image that's been debatable up to some extent. So you can see, at 300 kV, the electron wavelength is 2 meter, but we are talking about 0.8 angstrom, 0.5 angstrom in an average microscope. So we have resolution as is 1 order of magnitude smaller, but still it's a very good resolution. I mean, chemical quantities less than 1 angstrom. And these are actually the most dominant aberrations we see actually after some slides of the basic. Aberration, point is on the image plane. If you have non-perfect planes, and the point aberration is finite electric rate. Again, point is blurred. But if you have perfect planes, point will be image as a point. But this will not be point at the image plane because of the wave optics, you are going to have different limited self-comporting here, or the even better kind of so, in an abstract microscope, you can see there is a place for this confusion where the blurring can be reduced, or the effect of scale can be reduced. In fact, what's up we had just a piece here. It has two parameters in the abstract microscope, focus and the scales. So if you apply some of these on the focus, you can reduce the blurring from image plane to that plane to the confusion. So this is actually called structure defocus in an uncorrected microscope. Again, this slide is coming back because just to basically make the point here that so this spherical aberration actually is geometrical aberration. So we don't have any permanent loss information. To understand the geometry of it, then we can always retrieve the information. But if you have electromechanical vibrations, extreme magnetic field, and all sort of noise is coming from environment. So if you are not setting up the microscope properly, the room and the environment, then they actually come as infrared aberration or the parasitic aberration. So they come as the envelope, the field. And if the effect is severe, they start to multiple of the GS and lower spatial resolution. Contrast is important. I mean, contrast is nothing but the hydro intensities. So you have a good lens, but if you don't have good spec source, or if you don't have a monochromatic source, you basically reduce the significantly in field. Coming to the aberrations, so here is from geometrical optics, we can derive the C3 equal to minus half L0. L0 is the focal length. So you can see the C3, the most dominating aberration, actually is a less constant. Here is another way of visualizing or understanding the aberration. The point on the object going to the aperture plane and hitting the image plane, WI. So like supposed to form WI, but it's going to WI prime because of the imperfect lens. So the difference in distance actually is an image aberration. That's how we define aberration in this simplified way. So the geometrical aberration of the third order was first basically analyzed by Seidel. After third order, it is known as Seidel's aberration. The form of field spectrum, field curvature, distortion, and spherical aberration are the Seidel aberration. In the magnetic field, we have more aberration coefficient. The electron undergoes Larmor coefficient. These are some of the coefficients. We write all these coefficients in terms of symbols. And you can see the parameter omega and W0. So it actually indicates that some of the aberration depends on object position, and some of the aberration depends only on the scattering angle. It don't depend on the object position. For example, see the Seidel aberration, spherical aberration. Here, you can see a point will be blurred by this amount. And it is actually equal to the center of the object axis or to go away. It is the same effect basically everywhere and the image. So I already have mentioned the effect of CS can be reduced by structure defocus or by appropriate defocus for the corrected microscope by moving the image to the plane of this configuration. Coma, you can see coma spread will look like. You can see on optic axis there is no coma. But coma actually increases if you go away from the optic axis. And this is the azimuthal component because of the magnetic aberration for the coma. So you can see aberration figures for the field as spectrum and the field curvature. How the line will be blurred go away from the optic axis. And this is the combined effect for the electron in the magnetic. And last figure is your list actually is the distortions. So you can see two different distortions. In fact, they're important as well for the large field of your microscope. For example, the microscope which make use of the electricity. There you have to be basically more worried about distortion. We understand the geometrical aberration actually in terms of the warping of the spherical waveform. So if you have warping the spherical waveform, which is for sphere, you can see it's kind of warped. So basically you have aberration. And you write down this warping in terms of this function W, this is called the aberration function. And this W actually is kind of series expanded in terms of mini and the higher aberration coefficient. And third order you can see on defocus. C3 is basically spherical aberration. So in that way, we use series expansion and then we plot the PCF function. As you can see, for aberration vector microscope, you can see many higher aberrations. So nowadays you have basically when you have a microscope, you can correct up to fifth order. And the microscope we have in JLC, it will correct up to third order. So you can see all the aberration coefficients because you have to get factor into these symbols and all names and all because when you do when you do the microscopy, then you have to do the correction and then you have to come back to that slide after now on. The another notation. Coming now, I most of one time I'll go through quickly. So first aberration corrector was measuring structure and distance, cylinder and the volume state. So their purpose was to basically show that aberration correction works. Rather than actually improving the resolution of the microscope. And this is actually the corrector we have in the microscope called Rex corrector. It's a combination of two hexapole and then two transport outlets. And it is based on actually the concept of where the one being of one kind of basically lenses can be basically corrected by another kind of lenses by appropriately keeping them in series. And because of this basic invention and development, they are awarded not Nobel but Mukto. First prize in physics is your second highest award in physics in the year 2011. The details you can find from the references on the historical aspects of aberration correction. So there's many struggle and the funding issues and how the microscope modern day writer and they consider actually the first prize on the rise for the first man mission in the book. Nowadays, you can find both spherical aberration corrector and the chromatic aberration corrector. It is a combination of magnetic lens and electrostatic lens, which can correct both geometrical aberration and also chromatic aberration. So, microscope doesn't mean that you don't the lenses are corrected. It's a dynamic effect. Before you do imaging, you have to basically in our everyday morning, you have to do the measurement of the aberration, state of the aberration, and then you have to compensate them, and you lower the values below the specified the value to achieve a particular value of resolution. For example, 1 angstrom gives more the aberration coefficient below this value. So that is basically with the help of simulink W. So basically, you take a thin amount of carbon film and you accurately shape the series and you read the aberration coefficient like that. I mean, aberration reason you can see actually there is not circular all around the angle and particular shape actually has found to particular aberration coefficient. So you have to connect them and this is often done automatically. The concept of negative CS based contrast. In a corrected microscope, CS can be made 0. It can be made plus or minus value. So if you are making the PCTM plots, so if you are doing imaging the negative CS and the positive focus, your atom will basically appear right to white web. So you can see this is the image of zinc oxide done by us. Setting of negative CS, I can see zinc atom right to next time setting of PCTM the other way around, I can see zinc as a target. So the negative CS has been useful. Like R1 actually shows that now this imaging technique has been very useful. We image all the line atoms and the heavy atoms simultaneously together in a crystal, for example, lithium medium conductor. Where the directly image of oxygen jacket watering. So you can see oxygen atom along 100, but no oxygen along 010. So basically, you have defects. Of different ordering in the structure, and they have to do the property, for example, in this case, conductivity exposed. And a nice example for using a good coordinated monolayer, you can see E and N, and you can distinguish which is N and which is P, because N is the plus 2 atomic number more than boron. It is a little bit more bright. To quantify that, it will get what, and rest implies the defects. But there are different ways of doing quantitative imaging, HMDM and the Microscopy approach, and also newer methods are coming to mention. Some nice examples from literature. You can see here the image of nitrogen chromatograph. So here actually it is not really the imaging of the individual dots of atoms. Here actually showing one electron wave function. It means one electron of nitrogen having by surrounding carbon. So this is the example actually where we are picking up just next to the bonding information. Taking that. There is the example of magnesium oxide nanocrystal, where all the atoms have shape of single existing image. All the atom positions have been reconstructed, even the top and bottom surface. It is actually very much computational. It is a technique gives a lot of structural modeling to match into better. So image of holographic technique, but you can see old atom, and you can see some laserization of holographic changes. So this technique has the advantage that it can give you much simplified approach to physical reconstruction. It can give you space directly from the atom and also the input there. This is regarding for TPC, typography, etc. This was all these techniques are based in same mode. They also have these resolution, and this technique has been used in the image can write technically. So in this context, where we are basically working on the quantitative imaging, we encountered some difficulties in existing methodologies. So we published a set of motivation to publish this paper on the image simulation agent and also proposed some method actually for image reconstruction. So these are published in this paper. So if you find interest in the primary form, you can go to. So in case of image simulation, we have considered at white prism. And in case of the image reconstruction, we have actually simplified the equation. And that equation is applicable for the 2D vector and for field sample. And also the diffraction also, like I have another technique. We discuss in this all in details actually, because there are actually few different methods are available how to model that, how to model actually the beam atom interaction, and actually all depends actually on that, actually how phase flow and how phase flow should be exported in the image, and then that's how to try it. That is actually it gives you a background of the problem. So what happens actually the failure electron beam after going to sample undergoes the modulation into phase and amplitude because of specimen potential, and there is no oxygen exhibit. So we can record this oxygen exhibit either in diffraction plane or the image intersummation is also exhibit. And we need to recheck the schedules, like if you want to extend information, for example, the electronic properties, potential, etc., etc. And there are two types of schedules you have to follow the object space, display space, and the object space. So the papers behind the HFTM theory construction is very much elaborate. I mean, the main motivation for us is not in the entire topic, but just to mention that we have modified the equation in this form. And that actually very nice. Like when we applied actually on the monomer boronitride demo it through, basically extract the phase information straight away, and you can see the phase to the isolation of the atom, because actually atoms actually are considered as the phase object, so we can basically correlate on the phase shift to the atom number. Coming to last part, last two a couple of things. If you have information available on the diffraction space, if you don't have the UV capability, for example, X-ray diffraction, then you have basically phase is lost completely. And people normally use a Patterson pattern method, but in fact that actually if you do Fourier expansion of the FT or the diffraction pattern, you can retrace the image function. So I don't have time to go through. In fact, we have only diffraction pattern of the image similarity, that is, if I apply this equation, then I can get back the image. In fact, that is not exactly Patterson kind of synthesis, but it is actually direct fitting to give you the information. So, I mean, the photo HFTM is not only electron is where, but also we are trying to pursue the kind of bonds, the kind of fields, and the potentials. And why we are trying to do that? Because once we have potentials, we can really correlate with the material property. And nowadays we have development in terms of instrumentation and the direct detection camera. We have very high signal to noise ratio. And this structural property correlation of the images on the column potential actually that would be very beneficial, where you have theoretical methods actually in many cases they basically predict the properties So this is one of the very important goals. There are some groups actually they are doing active. So I'm done presentation. So here is the acknowledgement. Departments and also some funding which I made use to go to Bali and also all the students who helped me. I don't have any time to explain a lot of things. There are a lot of papers are there. I hope you would get some of the important points.
So we can have some questions now. So either people can raise their hands, or I think some of the questions are there in the chat as well. So I'll start reading that. So, so I think there's a first question. What is the mechanism of contrast enhancement in NCSI for simultaneous observation of light and heavy atom columns?
So this is actually phase contrast, and what Professor Natargon actually explained, I didn't have time to explain today, but normally I also have this answer. See what happens if you have negative phase contrast. How he explained actually, you add little bit of amplitude contrast with the phase contrast. In fact, that was actually helpful because of electron channeling effect. And so that was actually helpful to image the light atom and the heavy atom together in the single image. In fact, he published extensively. He also even made a Royal Society presentation. The usefulness of the technique, and yes.
Does anybody want to ask the question, or I can ask some of the questions which are in the chat?
Yes, if you can help me, I cannot see the chat.
Yeah. Okay, so there's one more question. How amplitude and phase are retrieved from off-axis electron holograms?
How amplitude and phase are?
Retrieved from off-axis electron holograms.
So again, I didn't have time to explain all this in half an hour talk. But in case of off-axis holography, the beam is split into two halves. One half is going through sample, and the other half is going through vacuum. And then you have biprism, by which you pull the two waves, basically interfere. So you obtain electron hologram. It's kind of the Young's fringes. And these fringes actually undergo bends if it sees any phase shift in the object. So from this bending actually, in a basic regular practice, what people do actually, they do the Fourier transform of the hologram. They obtain three bands, central band and two side bands, and they basically cut out one of the side band and do inverse Fourier transform to extract the phase and amplitude information. So it's more direct. But in case of inline or the HRTM, actually, the direct band and the side band, they actually overlap. So there is no way you can do Fourier transform and then extract easily. And that's why if you see all the methods based on HRTM, actually are based on through focal retrieval, and it's very you can elaborate and very tedious. And if that was a primary basic motivation for us to basically propose that equation, I mean to retrieve the information in a straightforward manner.
Okay. All right. So I think I can continue. So there's one more question.
Sure.
How aberration corrected HRTEM is used for defect visualization, especially oxygen vacancy in metal oxides for catalysis purpose? I mean, how is it different from HRTEM for defect visualization?
See, for 2D materials, the example I've given for boron nitride is much easier. You can directly see the one missing your defects, And if you have other kind of element, you can see, you can image as dopants, you can say dopants. But when you have 3D crystal, and in the 3D crystal, if you have certain thickness, and if you want to see dopants or defects, then the example that MgO crystal, whatever I showed quickly, so it's called atomic scale of tomogram. When you basically find out all the arrangements of atom. I know that there's a group in IIT Madras also has published similar kind of work. I think later on. So that will actually, you take a snapshot of the image, and if you have a good method, then you can basically retrieve, all the phase information. Where are the scatterers, And then you have the entire structure or the arrangement of the basically atoms in your hand, including defect, dopant, surface topology, And then you basically trying to understand why this catalysis or the catalyst is basically behaving in a certain way. No, it's no. Then it can do yeah. So in that way, no, but you can correlate structure and property of the material.
Okay, all right. Yeah, I think Mani has a question. Mani, go ahead.
So how easy it is to align the microscope and how stable it is? How often you need to align the system?
I'm sure the modern microscope will be okay, but I can tell you from my experience, our JNC microscope, like one of the basically first installation in the world. I heard that it was the fourth installation in the world, and like if I do alignment in the morning, it takes about 1 hour. I mean to do the alignment. If every other things are fine, then the state of basically correction stays okay for another few hours. So it to keep on basically measuring the state of correction. And then only like you have time to do some imaging, say for another half an hour to 1 hour. No, so all the time you have to keep on basically checking the state of basically aberration. So it's something actually not static; it's a dynamic thing. But I'm sure with the modern instruments, the timeline would be, or the duration will be even longer.
Okay, there are, I think, 2 more questions in the chat.
Sure.
The first question is, how do you account for residual aberrations may be responsible for misidentification of point defects in thick BN?
Residual aberration, I mean, I didn't understand what you mean by residual aberration. But if you see aberration coefficient and the aberration function, you have infinite number of aberration coefficients. So though you are predicting up to third order, there will be some higher order present, which will be the resolution limiting. No, but we should be happy about 1 angstrom, sub 1 angstrom resolution, because for point defects and all, actually we are interested to resolve how atoms are arranged. So we don't need actually anything better than 0.8 or like 1 angstrom resolution. No. So and up to third order correction is good enough. So it is not going to basically make any kind of what to say, a doubtful result. I mean, those things will be simply or directly visible. There shouldn't be any confusion in the result.
Okay. So there's one more question: how the intensity of BN of HR10 can be used to determine the phases of the material?
The phase, you mean the crystallographic phase, or so like which phase do you want? You mean?
So Sunny, if you can answer that ask that question.
What do you mean by phase here?
Crystallographic phase.
Okay, so basically I mentioned about 2 phases: crystallographic phase and the object phase. Here, so and this phase actually is a phase of the wave. That the wave actually basically picks up information about the object in terms of its in terms of the modulation. It undergoes into its amplitude and phase. No, that we refer as the object exhibit. So now this phase we have to retrieve to understand about the object, and the object we want to understand in terms of how atoms are distributed, and also we want to tell actually which atom is what. So how atoms are distributed in 3D, this is actually the this is called the crystallographic phase. Or diffraction pattern. No, but if you want to tell which atom is what, then you have to understand actually how individual atom has scattered, or how strongly they have introduced a phase shift. No, this we call object phase. So in fact that will dictate the strength of the diffraction pattern, or the intensity of the spot. So you have to extract this information in 2 different ways to understand how atoms are arranged, which will give you the crystallographic information. And if you can extract object phase, that also will tell you which atom is what. That means you have the complete information in your hand.
Okay. I think that's about it. I mean, if anybody has any questions, they can raise their hand or type it in the chat window. Okay, I think if not, then Manikandan, do you want to say?
Yeah. Okay. Thank you, everyone. Thank you, sir. And thank you for the.
Thank you, Manikandan. Thank you, Mamata, for hosting the talk.
Thank you. It was a great talk. Yeah.